Good afternoon, everyone. My name is Mark Dirks, and on behalf of ACRL and Choice, I'd like to welcome you to today's program, Connect the Library to the Lab, which is sponsored by Gale, a Cengage company. Today's discussion is one in a series of sponsored webinars from ACRL and Choice that addresses new ideas, developments, and products of interest to the academic library community. Free to users, these structured 60-minute live presentations provide the opportunity for interactive discussions of important new issues and developments in academic librarianship by librarians, vendors, authors, and other interested stakeholders. Before we get started, I'd like to point out a few features of the webinar software. In the main area of the screen, you can follow along with the presentation materials. Along the right-hand side, you should see a Q&A panel and a chat panel. If you don't, you can click the buttons labeled Chat and Q&A in the upper right corner of the screen to activate the panels. Please use the Q&A panel to submit questions to our speakers. At the end of the presentation, they will take a few minutes to answer your questions, so please do send them in throughout. If you experience any technical issues, please use the chat panel to let me know, and I'll troubleshoot the issue with you privately. Today, we're using the hashtag ACRLChoiceWebinars during and after this event, so if you have another screen handy, shout out to us. We're at choice_reviews on Twitter. Also note that we are recording today's program, and everyone who registered will receive a follow-up email with a link to the archived version. Our presenters today are Laura Messing, Jerry Sawchuk, Amos Patrick, and Angela Cannon. And here to introduce them today is Laura Messing from Gale.
Hi, everyone. I'm Laura Messing. I'm Marketing Manager at Gale, and I'd like to welcome you all to this webinar. Thank you for attending today. So we have 3 speakers for you today, and they will be sharing their insights on using interactive chemistry technology in the classroom. So our first speaker is Jerry Sawchuk. He is the Senior Director for Business Science Analytics in the academic market at Gale. Jerry has been in product management for over 35 years, the last 12 years in the educational publishing industry, having spent 9 years with Gale, in which he's developed over a dozen new products, and 3 years at ProQuest, where he was a publisher of natural science products. Our second speaker is Angela Cannon, a PhD and subject matter expert for the VivEd chemistry product. She has taken on an interest in how ordinary people understand and enjoy science and math since she was a summer tutor for a second-grade classmate in math. She has received her BS, MA, and PhD from Penn State in chemistry. She has experienced a variety of collegiate educational settings and textbooks. 8 of her mentors have authored collegiate chemistry textbooks or textbook supplements, and she has assisted on supplements for 3 different general chemistry textbooks and has spent 4 years at the University of Illinois teaching general chemistry courses and labs. While there, she edited, authored, and implemented course websites, online quizzes, in-house lab manuals, and exams for the 7,000-plus students to which she issued at least 1 letter grade. Finally, we have Amos Patrick, Vice President of R&D and Engineering and founder of VivEd. He received his master's in biomedical engineering from the University of Iowa, where his thesis was focused on using real-time game engines to visualize and accurately predict dynamic movements of the human musculoskeletal system. After graduation, he and his undergraduate advisor, Dr. Kareem Malek, teamed up to form Cyber Anatomy, which would eventually become VivEd. Over the last 10 years, he has been responsible for steering the technical direction of the company to create compelling, cross-platform educational applications with an emphasis on 3D interactive content. With that, I'll hand it over to Jerry. Jerry, please take it away.
Thank you, Laura, and thanks to all of you for attending today, taking valuable time from your schedules to learn more about how to connect your library directly to the lab through our new product, Gale Interactive Chemistry. I'd like to begin with a simple statement of fact. It takes on additional meaning for most of us. I'm having a little trouble with the slides here. Give me just a moment. Mark, maybe you can give me the access. Bear with us a moment, please. Here we go. Let's see if this does it. Here we go. Sorry for that. Little technical difficulties. So I'd like to begin with the simple statement of fact, and it takes on, as I said, additional meaning for any of us that have taken chemistry in college, and that's the statement, why is chemistry so hard, and what makes it such a challenging subject, more difficult than most of the other sciences? Of course, there are many reasons for this, and the literature commonly mentions the 5 that I have listed here. Number 1, specifically it uses math, and you have to be comfortable with math up through algebra to understand and work chemistry problems. Of course, geometry comes in handy, plus you'll want calculus if you take your study of chemistry far enough. Part of the reason many people find chemistry so daunting, though, is because they are learning or relearning math at the same time they are learning chemistry concepts. Number 2 is that it just isn't in the classroom, and a common complaint about chemistry is that it counts for the same credit hours as any other class, but requires a lot more from a student, both in class and outside it. You've got a full lecture schedule, plus a lab, problems, and a lab write-up to do outside of class, and maybe even a pre-lab or a study session to attend. And that's a big time commitment for most students. And while that may not make chemistry more difficult, it certainly leads to burnout a lot earlier than with some other studies. A student has less free time to wrap their head around the material, and having their library help with them with that can be quite a large advantage. Number 3, chemistry has its own language. You can't understand chemistry until you understand the vocabulary. There are 118 elements to learn, a lot of new words, and the entire system of writing chemical equations, which is its own special language. There's more to chemistry than learning the concepts. And number 4 is its scale. Chemistry is such a vast discipline. You don't just learn the basics and build on them, but switch gears into new territory fairly often. Some concepts you learn and build on, but there's always something new to throw into the mix. Always something old to review as well, so to make sure that you build a foundation on what you're learning for new. Simply put, there's a lot to learn and only a limited time to get it into your brain. And some memorization is required, of course, but mostly you just need to think. And if you're not used to working through how something works, flexing the student mind can take some effort as well. And finally, number 5, and that is chemistry is hard because we think it's hard, really. We've been told that. We've experienced it. We all know students who have failed chemistry. And if you think something is difficult, you're setting yourself up to fulfill that expectation. The solution to this is to truly believe you can learn chemistry. And if, as a student, I knew that my library had a resource that makes chemistry easier, would I use it? Well, of course I would, and I tell other students about it as well. So our problem hypothesis on chemistry as a problem of being so challenging and on creating Gale Interactive Chemistry for the Library is that students experience difficulty in fully and appropriately understanding the fundamental concepts of chemistry. Why? Well, because chemistry is based on assigning meaning to the unseen and the intangible. We believe that not a lot of chemistry products in the library help a student with this. So let's take a look at that. What's available in your library? In academic libraries across the nation. And of course, I caution this is only a sample. There surely are ones that I've missed. But these are primarily databases for chemistry research, either through traditional e-books, scholarly journals, and some libraries have access to products that provide the structural approach to chemistry, products like ChemSpider, PubChem, ChemBioDraw, to name just a few. We hope that you will like what we have to show you this afternoon, of course, as we believe it is quite different yet. But I want to make a point here, and that the purpose of our product here is to supplement, not replace any of your core chemistry products. So let's take a look at what's available to teach and learn chemistry, because there's some other things on the internet that may be used in classrooms, and a few of them are shown here. But in an age of technical advancement, there's a limit on what is available in helping students in learning basic chemistry concepts. You've got PhET, you've got a lot of periodic tables that tend to be somewhat defined as interactive. And again, I'm sure I've left off some of these products that maybe your faculty or even you use in the library. I apologize for that, but my point is there's not tremendously a lot available, and the quality of it is pretty low scale. So the question, can technology help? And one hypothesis we are setting out to prove is, can technology help students learn chemistry? So let's take a look at some of the literature or research on this, and it may be difficult to read, but I'll try to pull it out for you. On the left is an article from Computers in Education, and granted it's a bit dated, but still pertinent even today. It takes a look at research from the period of 2002 to 2012 on this subject and concludes that there is robust evidence that computer simulation can enhance traditional instructions, especially as far as laboratory activities are concerned, and that's the point of our discussion today, connecting your library to the lab. On the top right is a study at the University of Illinois at Chicago Learning Sciences Research Institute. And with a grant from the National Science Foundation, they studied the impact of using physical models in organic chemistry, not exactly the same as computer models, but still pertinent. The key conclusion they found is that models are helpful, providing students can handle, or in the case of computer models, interact with them. So actually showing them without this interaction actually proved to be a negative impact to the learning. At the University of Rochester, and this is on the lower right, they essentially arrived at the same conclusion, quantitatively measuring an average improvement of anywhere from 16 to 26% improvement in scores with the use of model kits. Again, interaction with the kits appears to make the difference in the scores. This is, of course, not all of the literature, but it's meant to give you a flavor of the conclusions that was reached. This next article is from EduCause. It's a nonprofit international association of IT leaders and professionals committed to advancing higher education. You may be familiar with them. Ben McNeely from North Carolina State University talks about the net generation, those born between 1982 and 1991, who have essentially grown up in an environment in which they are constantly exposed to computer-based technology. Over on the right, I made a note, a little box, difficult to see, but it defines iGen, Gen Z, millennials, and all these categories. It can get a bit confusing as to the labels that we place on some of these generations. Suffice it to say, though, that my kids and my kids' kids, of course, growing up in computer age and technology is such a key part of their life. But McNeely makes the point that net genners learn from doing, and what net genners want from learning technology is interactivity, whether it's with a computer, a professor, or even a classmate. They want it, they crave it. Traditional lectures are not as fulfilling to the learning potential of typical students today, especially when they've been brought up with technology in their everyday lives. So interaction, technology, it's everywhere. So we ask ourselves, why isn't it more tightly integrated in learning difficult subjects specifically like chemistry? Well, of course, there are challenges in funding as technology costs money. It also needs to be easily accessible, relevant, and interactive to the coursework being taught. These are all key considerations when considering using technology, and in our discussion specifically, using the technology with a subject like chemistry. So we ask ourselves the question again, can technology help, and can it help with learning chemistry? We at Cengage believe that it can, and we've taken steps to try to do just that. So we've created an affordable solution with easy access to all by placing this resource in the library, connecting the library to the lab, in effect, with an interactive and relevant learning tool to what is being taught. So let's now turn to the product itself, Gale Interactive Chemistry, and I'll briefly cover a few of the major features before Amos and Angela will do a demonstration for you by getting actually into the product to see what we have here. One of Gale's primary objectives of our interactive products, however, is to provide a solution for both auditory sequential learners who are step-by-step learners and therefore appreciate a session-based organized learning path, and the other visual spatial learners who just want to dive into the whole picture and explore things on their own. Our objective was to accommodate both types of learning, and we currently offer 2 interactive products for academics, human anatomy and chemistry, which are shown on the screen here. They're similar, but they're actually quite different in terms of how they approach the material. Human anatomy focuses on the visualization of the parts of the body and how they relate to other parts, whereby chemistry is simply a product that brings the unseen to being seen. The ability to actually view atoms, molecules, and through interactivity with the models, experience cause and effect relationships of the chemical elements. As the student opens any session, there will be a viewer, and we're looking at the product now on screen. On the left, you can see that there is a visual area for the 3D interaction. It's part of the entire model screen, but you can expand on that, and you'll see that in the demo if someone just wants to interact and go into the model session. For the visual spatial learner who just wants to dive in, or for use in the classroom by the teaching professional, they can simply expand the screen to full view, as I said, and begin exploring at any time. For the opposite, the auditory sequential learner, there are over 150 learning sessions which are progressive by advancing the lesson by clicking either on an arrow on the right hand of the screen, or also on the bottom of the screen there are progression dots which tell a student exactly where they are in the session. In addition to lessons and progressive material being presented, there's also quizzing included, several different types after sessions, so we can measure exactly what the student is learning and what they may need to go back and reiterate on. The interactive content is supplemented and coupled with authoritative reference content from Gale, and this is done in multiple ways. As you can see from the screen on the right-hand side, and I won't demonstrate it here, but as a lesson progresses, the text on the right will change as the lesson is given. So that's one set of content that teaches the student in addition to having an interactive model. Also, a student can actually go in and do a search. As you can see, I've expanded that, and they can actually go in to search both reference content as well as periodical content, which is included within the product. So there's some content behind the screens in addition to the model to do traditional types of research. In addition, the student can also link the content through interactive interlinking, and this is available on most of the Gale products, but this allows the library to expand on other content by allowing the student, when they're looking at clicking on any of these hyperactive, you see some of those in blue on the right, they actually will be able to open up other content that's in the library, specifically in the Gale Virtual Reference Library collection, and then to click on one of those and actually open up the actual article in the database within the library. In this particular case, you can see kinetic theory of matter. So this allows you to leverage other content within your library. It allows you to customize content by buying certain e-books that you may wish to include as part of the product. It's important to note that this content that is being surfaced within GVRL is keyed to the subject. So when searching on something like iron, you're not going to get, let's say, a story on Iron Man, which may be in a fictional book that you may have in your GVRL library. It sticks selectively within health and chemistry content. So that's all I have in order to show you an overview of the product. I'd like to turn it over now to Amos Patrick to provide, and Angela, to provide some examples of some of the models and how the models work, and you can get a really good feel for exactly the type of product this is. So, Amos?
All right, thank you, Jerry. So I'm going to start out today talking about radioactive decay. This is typically a second semester chemistry topic, but it's often avoided because the lab work is dangerous and the half-life times make it difficult to kind of explore this topic. So we feel like this is an excellent example of bringing the library into the lab. So let me start out by showing you an example of how a student can interactively study radioactive decay sitting in the library. So here we have our workbench, and it's fully interactive. And what I can do is I can select any element on the periodic table. So here I've selected calcium. And if I zoom in, what we have here is a visual representation of the nucleus of this particular isotope. So like I said, I've selected calcium, and in particular, I've selected calcium-39. So because the atomic number of calcium is 20, I know that there's 20 protons, or these blue spheres, inside the nucleus. And because the atomic mass is 39, I can figure out that there are 19, neutrons in this nucleus. On the left side over here, I've got some other common isotopes for calcium. So for example, if I were to click on this calcium-45, pay attention to what happens here on the nucleus. You'll see what happened is I've added more neutrons, and that's because our atomic mass has jumped up to 45. Our atomic number is still 20, we're still calcium, but now we have 25 neutrons in the nucleus. So let's get into some radioactive decay. I'm going to go down here and pick uranium-238. This is kind of the classic uranium decay path that students are asked to study. So this particular isotope, it's going to undergo alpha decay. And this can be seen down here on the workbench because the alpha button is lit up. And what we can do is we can interactively decay this nucleus. So what I'm going to do is I'm going to click this alpha button over here, but pay attention to the nucleus. I'm going to zoom in on it when I click it, and we'll see what happens to the nucleus. So I clicked it, and look at that. This is called the alpha particle. And an alpha particle is composed of 2 neutrons and 2 protons. So this nucleus has lost an alpha particle. I'm going to zoom up here and look on the map, and this is going to be our decay map. This is going to show us how this isotope is decaying. So what we've got here is up here we've got uranium-238. This is the original element that we started out with. On the x-axis, we're showing the atomic mass, which is 238. And on the y-axis, we're showing the atomic number, which for uranium is 92. Now you can see we did an alpha decay. And so we lost 4 things. We lost 2 neutrons and 2 protons. So that reduces our atomic mass by 4. So you can see we've jumped from 238 back to 234. And 2 of those things that we lost were protons. So our atomic number has dropped from 92 to 90. So we've actually changed elements. We're now thorium. If I look down here, we are also showing the decay path down here. These little circles show us the states that we've stepped through. So we started out as uranium, and then we went to thorium. And you can see down here on the periodic table, our game piece is moving to indicate to the student that you've changed your position on the periodic table. Okay, so now we're thorium-234. This isotope wants to go through a beta decay. So remember, we're following this chain of decays. So this is going to do a slightly different decay method. This is going to do a beta decay. So again, I'm going to click this button, but let's watch what happens at this nucleus. So I'm going to click the button, we zoom in here, and look at that. It's a neutron is getting converted into a proton, and then it's releasing an electron. So let's see what that looks like on our map. So this is what a beta decay looks like on our map. You can note that the atomic mass is constant, right? We didn't lose anything except for that electron. And that electron doesn't really, it's negligible when it comes to considering atomic mass. But we converted one of our neutrons to a proton. So our atomic number has now bumped up to 91. So we're a new element. We're protactinum now. So if I come back down here, you can see we went from thorium to protactinum. Now this element, or this thing, will continue to decay. There's a beta decay, for example, and so, you know, we're going to bump back over to the right. Then this isotope, so now we're back up, we're uranium again, but we're a different isotope. We're uranium-234 now. It wants to go through an alpha decay, et cetera, et cetera. I won't run through the entire decay series, but what a student is often asked to do is to map this out on a piece of paper. And so here's an example of a homework assignment that could be done in the library. A student could be asked to write out the decay path of uranium-238, or draw it out using this. And this decay path is not, they're not always just one path. This particular path has a few forks in the path, and so the student could be asked to chase down each of those paths, each of those forks, and graph that out. They could also be asked to explore the decay path of some other isotopes, such as plutonium or carbon. So we all understand the importance of a nuclear reaction, but the vast majority of chemical reactions that we see in the lab actually happen in the electrons. So Angie, I'm going to pass this over to Angie now, and she is going to show us an example of how students can study electron orbitals.
Thank you, Amos, for showing us nuclear reactions. And Amos is correct in the fact that reactions, actually, most reactions that we experience happen on the electron level. So we're going to take a look at atomic orbitals. Atomic orbitals are the description of the probability of finding an electron around the nucleus of an atom and where those electrons are. And students study this beginning in intro chemistry all the way through graduate school. A physical chemistry student might do an emission spectroscopy experiment. Here we have a picture of that experiment where we have a gas tube filled with hydrogen. The light from it passes through slits in a prism, and then it's detected on a detector or a film strip and gives what we call a line spectrum. Each line spectrum is characteristic of each and every element on the periodic table, and as citizens, we're used to experiencing this in fireworks displays. So atomic orbitals and quantum numbers define the regions and the arrangement of the periodic table. So here we have one way to depict the periodic table in which we have the s orbitals. There are 2 elements wide in the s block of the periodic table. Then we have the p block over here on the right-hand side, which is 6 elements wide. The d block, which is 10 elements wide, and then the f block, which is 14 elements wide. And we see this in the actual atomic orbitals for each and every element. So the quantum numbers have, there are 4 quantum numbers. There are the principal quantum number, which corresponds to the period of the table. Then we have the angular momentum quantum number, which corresponds to the shape in 3D space. And we have a magnetic quantum number, which corresponds to the orientation mathematically defined as x, y, and z. And finally, the spin quantum number, which means there can be up to 2 electrons in every atomic orbital. So that's why in the s block is 2 wide because there's 1 elements wide because there's 1 s orbital in each period. There are 3 p orbitals in periods 2 and above, and that's 6 elements wide. There are 5 d orbitals, which are 10 elements wide, and 7 f orbitals, which are 14 elements wide. So a freshman student would be introduced to atomic orbitals with the s orbitals, which are spherical. And again, an orbital is the probability of finding an electron around the nucleus. So one of the first things that freshmen learn is that as you go up in principal quantum number, the probability of finding that electron gets further and further away from the nucleus of the atom. The next thing students learn is about nodes. Nodes are regions of zero probability of finding an electron. So the only orbital that does not have a node is the 1s orbital, because the number of nodes in an orbital are always the principal quantum number minus 1. So 1 minus 1 is 0, but every other orbital has nodes in it. So here we have the 5s orbital, principal quantum number 5. So we should have 4. We should have 4 nodes within this orbital. So we can see that here with this slice through our set of spheres, with the pink to green region being 1, the green to pink region being 2, the pink to green region being the 3rd, and then the green to the pink region being the 4th. Next, students learn about p orbitals, and again, just like the s orbitals, as you increase in principal quantum number, the probability of finding the electron is further and further from the nucleus. Students also learn that the p orbitals all have one planar node, and this is a non-radial node, and it is seen here with the fact that this orbital is oriented on the y-axis and the xz plane is the planar node. You can look at one of the other p orbitals, this one being on the x-axis with the yz as the planar node. Then a physical chemistry student, so graduate or undergraduate chemistry major, would further learn that this still again applies. The principal quantum number minus 1 is the number of nodes in every orbital. So we have one planar node because this is a p orbital, yz, and we have 4 radial nodes for a total of 5 nodes. So here's one radial node, a second radial node, a third, and a 4th radial node to come to 5 nodes total in the 6p orbital, this 6p orbital. Finally, as freshmen, they also see the depiction of d and f orbitals. D orbitals have 2 non-radial nodes. Here we see those as 2 planes. We can also see that as 2 cones, so we get this donut structure around the 2 lobes there as 2 conal nodes. In f orbitals, let me give a better view here. For f orbitals, there are 3 non-radial nodes, so we see that here as 3 planes. Here's 2 planes. And if we pan around, we see the 3rd plane. And we can also see that that happens as a plane and 2 cones. So we have our plane here and 2 cones out from the nucleus of the atom. So atomic orbital theory really leads to the bonding and also the trends within the periodic table. And Amos is going to further explore trends for us in the periodic table.
All right, thank you, Angie. So yeah, as Angie just said, understanding property trends in the periodic table is foundational to understanding chemistry. As an example, we're going to explore electronegativity. So electronegativity is an atom's ability to pull a shared electron towards itself. So here we are kind of graphing out the electronegativity value for each of these elements. What we want to convey to the student is the trend of electronegativity as we move around on the periodic table. So let's kind of examine this by, yes?
Excuse me, Amos, this is Mark, just jumping in. I think we need you to share your screen once again.
Oh, I'm sorry. Must have hit the wrong button. Let's try that again. There we go. Okay, I'm sorry. You guys seeing my screen now?
Yep.
Okay, cool. So here we are looking at the periodic table. And we're showing the electronegativity. Essentially, we're using the elements as column graphs to show electronegativity of the periodic table, or of these elements. And what we're trying to convey to the student is the trend of the electronegativity as we move around on the periodic table. So let's try to isolate this down to a group. And let's just kind of talk real quick about what electronegativity does when you move across a group or you move down a group. What we see is we see a strong drop-off in electronegativity. And this is primarily due to electron shielding and atomic radius. So we can visualize this by clicking on, say, fluorine here and looking at our trinket. And what we can see here is fluorine's got about, it looks like around 9 electrons surrounding it. Now, if we were to step down to the bottom of our group and look at this last element, we see this element has a whole lot more electrons surrounding it. So these electrons are creating a shield, or they shield out that pulling power of the nucleus, which is trying to attract that bonding electron. So that's why we're seeing that step down. It's also related to atomic radius. So if I were to graph these guys based on their atomic radius, you see that atomic radius, these elements get bigger as you step down a group. And the bigger the radius of the atom is, the less effective that pull from the nucleus is. All right, so that's looking at it in terms of groups. Let's look at electronegativity as it moves across a period. So here we are looking at the period, and what we see is the trend is a slight increase as we go from left to right across this period. So this trend is largely driven by the number of electrons in the valence shell. If a valence shell is primarily empty, it takes less energy to donate the electron than it does to gain one. So we can look at that by clicking on potassium here. And let's go in and look at its electrons and how they're surrounding this guy. So what we have here is we see this one lonely electron out here on its outer valence shell. Now, since this element's valence shell is almost completely empty, it doesn't have a lot of desire, I guess, to pull another electron towards it to try to fill this shell. But as we step across this period, you'll see more and more electrons will get added to that valence shell. And as this valence shell gets filled up, the desire of that element to pull an electron and add more electrons to the valence shell increases. So let's jump all the way over here to bromine. Now, if we zoom in, bromine has one lonely hole left in its outer valence shell, and it's just desperate to fill that. It really wants to fill that. So it's going to pull hard on those shared electrons. We can also take one more step and look at our noble gases. So this is krypton down here, or krypton down here. And if we zoom in, what we see here is its valence shell is completely full. And so that helps us understand why we get this sudden step off. This element, these noble gases, they're completely satisfied. They have no desire to share electrons with anyone, so they don't tend to bond. So why is this important? Why does the student need to be able to know this? Well, knowing the difference in the electronegativity between two bonding elements allows us to understand how those two elements are going to bond. Essentially, if there's a large difference in the electronegativity between the two bonding elements, you're going to get an ionic bond. But if there's not so much of a large difference, you're going to get a covalent bond. So let me turn this off, and let's just talk about two bonds real quick, two common molecules that we find. Let's talk about salt, which is sodium bonding with chlorine. And we can just look at their position now on the periodic table and know, okay, chlorine is going to have a really strong electronegativity value, whereas sodium is way over here on the left. So it's going to have a relatively low electronegativity bond, or an electronegativity value. And so their difference is pretty big. So these two are going to probably bond through ionic bonding. Now, if we were to think about carbon dioxide, which is the bonding of carbon and oxygen, we can just look at the table now and say, well, these guys are actually pretty close to each other. So their electronegativity values are probably not that much different from each other. So we know that these guys are going to bond through a covalent bond. All right, so now I'm going to pass this back to Angie, and she's going to discuss that now that we know how these elements are going to bond with each other. She's going to show us how we explore the nature of these bonds by looking at reactions.
Thank you, Amos. So yeah, students are able to look at reactions in the lab and in demonstrations, and there are several reasons that they may not be useful in aiding learning, and one of those might be that it's not visually interesting. We had the example of nuclear reactions, which were too toxic and dangerous, and also impractical timescales. Well, that's the case on other reactions also. But we can also bring some of these more dangerous reactions to the students in the lab, or maybe the visually uninteresting ones, through the library. And we do that with our simulation here, and we see the balanced chemical equation in this reaction. We also see all the molecules, the reactants, and the products depicted correctly here. And we get the color-coded key of each of the elements in those reactants. And we'll have the molecule view of this reaction and the actual lab view of this reaction for the students. So we can see if we zoom in here, as Jerry said earlier, one of the things about chemistry that's really hard is chemistry is a language, and a balanced chemical equation is almost a paragraph to a chemist. So we have ammonium dichromate, which is a solid. One molecule of that will react to form one molecule of nitrogen, which is a gas, 4 molecules of water, which are a gas because this is an energetic reaction, and a molecule of chromium-3 oxide. We can zoom in on our actual reactant, our ammonium chromate molecule, and see that ammonium is the NH4 part. So we have the blue dots sticking through, 2 of them sticking through 3 hydrogens. And if we pan around, we see that the 4th hydrogen is underneath there. And then we can also look at the Cr2O7 part and pan around and see that the gray-blue chromiums are there. There's 2 of them in each of the molecules, and they are surrounded by 7 red oxygen atoms. So if a student then clicks on our molecule, our starting molecule, they can watch the reaction, and we see that we get 1 nitrogen molecule, 1, 2, 3, 4 water molecules, and 1 chromium-2O3 molecule, which is a solid and dropped to the floor of the laptop. The student can do this again several times, and each time they are, the reaction is governed by the law of conservation of matter, so they get 1 nitrogen molecule, 4 water molecules, and 1 chromium-3 oxide. We can look at another reaction like this, and the fact that this is governed by a balanced chemical equation. When we look at the ammonia reaction, where we have 1 nitrogen reacts with 3 hydrogen molecules to form 2 ammonia molecules. And a student can connect these, and let's say they connect the wrong number of molecules and nothing happens because they didn't follow the balanced chemical equation. So they're learning how to read a balanced chemical equation prior to even having to balance a chemical equation. And then they get to watch the animation of the product being formed, which is 2 ammonium molecules each time. This reaction also happens to be reversible, which is indicated by this double arrow. And a reversible reaction means that we can take the products and form reactants. So I can take 2 ammonium molecules, and it tells me that the reverse reaction needs heat, so I can apply energy as a source of heat, or heat is a form of energy. And then I can watch the reaction go in the reverse direction. So Amos is going to continue on with balanced equations for us, because students must be able to balance an equation in order to be able to know the amount of reactants they need to synthesize anything in the lab, and therefore determine their product yield at the end of their experiment. Amos, you're muted.
All right, thank you, Angie. Hopefully I shared my screen properly this time. Okay, so as Angie said, knowing how to balance an equation is another fundamental skill for all chemistry. It's also one of those skills that just takes practice. I'm going to demonstrate how a student can practice this skill in an interactive way that's really focused on driving home what is physically happening behind this equation, this language, this sentence that we're using to describe a reaction. So in this reaction, we've got two molecules on the reactant side. We're going to combine C8H18, which is octane. It's this bigger white one over here, with a certain number of O2 molecules, this pair of red ones. And these are going to react, and they're going to form a certain number of carbon dioxides and a certain number of water molecules. Now, as a student, what we have to do is we have to figure out, what are these numbers? How many octanes do I combine with how many oxygens, and then what am I going to get out of this? Or how many carbon dioxides and how many water am I going to get? So let's just start by adding one of each of these molecules to each side of the equation. And I'm just going to go ahead and try this. Maybe this is right. Maybe we just need one of each. I'm going to hit check, and it flashes red. It indicates to me that, no, this is not right. This equation is not balanced. And if we look up on the board, we can see why. What we have to do is we have to obey the law of conservation of matter, which tells us that you have to have for the exact same number of each of these elements on both sides of the equation. So you can see, for example, for hydrogen, we've got 18 hydrogens on the left side of this equation because we got this big octane in here, but we've only got two because we only have one water molecule on the right side. So we have to balance this out. So let's do this interactively. I'm going to start out by balancing the carbon. I'm going to skip oxygen for now because you see oxygen shows up in more than one molecule, and that just makes it a little harder to balance that way. So we're going to start with carbon. And the way we introduce carbon to the product side is through carbon dioxide. So let me add a bunch of carbons, and I'm watching this graph right here in the middle. And now I can see that the carbons are balanced. You have 8 carbons on the right side, and you have 8 carbons on the left side of this equation. Next, let's balance the hydrogen. We can see we need more hydrogens on the product side. So I'm going to add some water molecules in. So you can see I'm adjusting the hydrogen count. I'm also messing with the oxygen balance up here too. Okay, so now we have carbon and hydrogen in there. And now let's add our oxygen molecules in. So here we go. I'm going to add a bunch of oxygen molecules in. And we're going to balance this out. But we run into a little bit of a problem here. If we count these up, we actually have 25 oxygen molecules on the right side, but only 24 on the reactant side, on the left side. And I can't just add one molecule in because they come in pairs. So if I add one more of these, I have too many on the left side. And then you start chasing your tail because the only way you can add a H2O you can add one oxygen over here, you end up adding some hydrogens. So let's take a step back and think about it. What this tells me is we need to double everything. So I'm going to add another octane. I'm going to go back and balance the carbons again. I'm going to balance the hydrogens again, just like we did a minute ago. And now I'm going to try to balance the oxygens again. And there we go. Now we got it balanced. I'm going to hit the check button, and it flashes green and lets us know we got it right. So what we've done is we've balanced this equation. We need to combine 2 octanes with 25 O2 molecules. And what we're going to get out of this is 16 carbon dioxides and 18 H2Os. To really drive home that we're having to obey the law of conservation of matter, we reveal to the student this reaction slider. And what it does is it allows us to slide these back and forth now that we've balanced it. And the whole point of this is to really demonstrate to the student, hey, look, these are not two different things. These are the same oxygen molecules on the left side are on the right side. Nothing is added, nothing is lost. When we react to these things, we're just reorganizing the same pool of atoms. All right, so I'm going to pass this back over to Angie, and she's going to talk about another major class of reactions studied by students, especially those heading into the medical field, and these are organic reactions.
All right. Thank you, Amos. So yes, organic students spend half of their time doing synthesis reactions, and therefore they must calculate yields and need to be sure that their equations are balanced in order to do so. But organic students study chemistry, especially a lot of pre-med students or medical-oriented students study organic chemistry. And in organic chemistry, students see the two-dimensional schematic of all of the reactions, and they are suggested to use 3D models kits in order to help understand the three-dimensional aspects of an organic reaction. So here we are able to simultaneously show the 2D schematic and the 3D animation of the reaction to a student, or a professor is able to show it, or the student is able to explore it on their own and know that their 3D model is accurate according to the schematic. Here we have the reaction of ethanol with hydrobromic acid, and we can see the lone pair represented both in the 3D and the 2D models. Will grab a proton from the solution. As that grabs the proton, we note that the carbon and oxygen become partially positive in the organic molecule, which allows the negative bromine to approach that carbon. And we end up with this intermediate or transition state where the molecule is a trigonal biplanar molecule. And finally, the water group leaves to give our product of bromoethane. And note that at the beginning of the reaction, this methyl group is pointed towards the right-hand side of the laptop, but it goes through this transition state, which is a particular mechanism, and then that methyl group points to the left-hand side of the laptop. And when a student looks at stereochemistry later in organic chemistry, they will need to be able to understand that that mechanism leads to the flipping of that methyl group from one side to another. Another quick look at a different organic reaction which happens on the absorption of a physical surface is ethane to ethene, and it's going to lose its hydrogen atoms by bonding to the platinum surface. And physical chemistry students and analytical chemistry students often study these type of reactions both in as undergraduates and graduate students for chemistry. So we hope that you have appreciated a tour of how we can bring and connect the library to the lab.
Thank you, Angie. This is Mark. I think we have a few moments here at the end of the webinar for some questions. So I will turn the floor over to Laura to handle those questions.
Okay, thanks, Mark, and thank you to Jerry, Angie, and Amos for that insightful presentation. And you can learn more about Gale Interactive Chemistry and see how you can get in touch with a Gale representative to continue the conversation at gale.com/interactivechemistry. So now I'd like to open it up to questions, and you could submit them through the WebEx tool. And we did have a question come through during the presentation, and this one is for Jerry. So this person asked, we recently added the human anatomy product after getting feedback from our faculty, and our LMS is Canvas. are there any plans for developing LTIs for these products to make it easier for faculty to incorporate these into their courses?
Yeah, thank you, Laura. That's an excellent question. We are seriously looking at different ways because the product is in the library, and obviously as we talk here, connecting your library to the lab, it's important that we be able to ingest these and have some integration with local LMS systems used in the classroom. Available now, no, but that is on the planning horizon. And certainly I know that the Canvas is one that was mentioned here. I think they also have a good way to do that, but certainly welcome any input with the types of LMSs you have and are using so that we can prioritize which ones we take a look at first. Thank you.
Okay, great, thank you. I've got one for Angie. So Angie, how might the library help a professor implement this new platform?
Obviously, the professor could most easily just introduce the student to the fact that the product is available in the library to help them study, but it really works best when the professor can point the student to some of the activities and the different simulations for the student to use along with their course, either by linking it to their homework, possibly using it to flip the classroom a bit, use it maybe to introduce or wrap up a subject in the classroom. And so those are effective means to get to more of a guided inquiry about chemistry instead of just simply presenting the topic to the student to memorize.
Okay, thank you. We've got one for Jerry. So Jerry, can Gale Interactive replace lab work?
Well, thank you, Laura. Studies have shown, of course, that these types of learning tools are more effective for really the conceptual understanding of things. However, there are many goals, and it depends on the faculty and the types of labs that they're doing. We certainly aren't postulating here that they replace lab work, but rather, as I said earlier on, is to supplement not only materials in the library, but also to supplement lab work, because as a student goes in, maybe only has certain time to physically spend in the lab, but they may have more time back in their dorm room or going into the library, and it can actually repeat a lot of those lab-type experiences through a product that's now available through their library and easily available to get to. So, again, we don't recommend, although in some cases maybe there are in some very common situations where they may be able to replace a lab exercise and getting to more advanced types of things, but that's not normally what we've designed the product for.
Okay, thank you. We've got another question that came in. Is this only through the library, or could this be through the chemistry department? And I'm thinking of funding and budget.
Yeah, certainly. We have it available, and I think it probably lends itself more to a library or a large department availability. I think the large difference here in terms of the business model is it's not actually sold to individual students like a textbook or anything of that nature, or even sold to a faculty classroom. But if it makes it easier, certainly, for funding purposes, to have another department pick that up and then make it available, and maybe perhaps they would fund it and allow it to be in your library, then that's a boon for all involved in order to promote it as much as possible.
And then we have another question here about can this be accessed by students via Canvas set up by professors?
Well, that's you're talking a learning management system again, and it can be, and it is available through the open web in a URL. We also very shortly will have the product available on desktop versions, and you can actually link to specific sessions or specific slides within the sessions through URL linking. So a professor could either place that within their syllabus or within the Canvas portion of that area that a student can actually access and then call it up from there. So certainly that's doable.
All right. Well, that looks like all the questions that we have for today. And if you have any more questions, you can always send us a note through gale.com/interactivechemistry. And now I'm going to hand it over to Mark.
Thank you, Laura, and thank you, Jerry, Amos, and Angela for your presentation. This is Mark again from ACRLN Choice. I just wanted to say thank you, as we have to each of our presenters, for spending time with us today and for sharing this product and your insights about it and chemistry. And I would just remind our viewers that we did record today's program, so be on the lookout for a follow-up email from ACRLN Choice with a link to the recording. And thanks again to all of you out there for joining us today. I hope you enjoyed the session and have an excellent rest of your day. Thank you very much. Bye-bye.